Okay, so what we're going to do today is just to go through the homework that I assigned over the break, and then I'll answer any additional questions that you guys have. But if there's problems hearing me, like I said, I'm not using the usual microphone. I'm using the camcorder, so if there's something I need to adjust, just let me know. Okay, so the first problem from the homework said you're meant to consider some pipe and some marble that you're dropping in this pipe, where the marble has some charge given to it, Q, and some mass of M. And what you want to find is the force that the marble acts on the pipe as a function of time. If there is some constant magnetic field, we'll say V0, that points to the right. Okay. So right off the bat, what we see looking at this, we have some magnetic field pointing to the right. When we drop this marble, because there's no friction between the marble and the pipe, this is just going to fall with some velocity that we don't know yet, that we can write for now just as V. Ultimately, we want to find a force, and seeing that we have this velocity and this magnetic field, that's going to lead us to want to use the Lorentz force law. So that's to say that the force is going to be equal to Q V cross B. There's no electric field, so we don't have to write that term. Okay. So now, the first thing we can do is determine what the direction of the force acting on this marble is. And so in order to do that, we can take the fingers of our right hand and point them in the direction of the velocity of the marble, and then curl them in the direction of the magnetic field. So here, my fingers are going down because the velocity is down, and I'm curling to your right because that's the direction of the magnetic field. My thumb is going to point in the direction of the force. So we know that the force ultimately acting on the marble is going to be pointing out. Okay. Now, in order to evaluate the rest of this equation, what we need to do is we need to know what Q is, what V is, and what B is. Luckily, we know what Q and B are because they're given, but we're not told what V is. So in order to determine what V is, what we want to consider is the fact that this is falling only under the influence of gravity. So if we were going to draw some free body diagram, this would be the only force acting on this marble. And so, at least in this direction, we're not really interested in what's happening with the magnetic force. It's going to cancel with some normal force from the inside of the pipe. But in terms of its motion, the only force that's causing motion is going to be this force of gravity. So what that says is that the acceleration is just going to be the acceleration due to gravity. And what I'm doing is I'm defining down to be the positive direction. And so because we know the acceleration is going to be related to the time derivative of the velocity, which in this case is going to be just our acceleration due to gravity, we can multiply both sides by dt and integrate. And when we do that, we see that the velocity as a function of time is just going to be equal to the acceleration due to gravity times time. In principle, plus some constant integration, but because we're dropping this marble from rest up here, that's to say that the initial velocity is 0, so that that constant of integration is also 0. Okay, so now that we have this velocity, we're ready to evaluate the rest of this equation. This says that the force acting on the marble is going to be QV, which is G times T, times the magnetic field, and this is going to point out. But the question doesn't actually ask what the force on the marble is, it asks what the force on the pipe is. And so because the marble is moving down through this pipe, it has some magnetic force pointing out. But it's constrained to move in the pipe, and so the pipe's preventing it from moving in that direction. There's going to be some normal force acting on the marble to oppose that, that motion. And that normal force ultimately is going to be the same thing as the force that's acting on, that the marble acts on the pipe. And so that's to say then that the force acting on the pipe is, well, hold on, let me think. So the force that the marble acts on the pipe is going to be this way, and so the force that the pipe acts on the marble is in the opposite direction. And so the force that the pipe acts on the marble is going to be QGT B0 out. So this is the force the pipe acts on the marble. Okay? And so there was a question earlier in class concerning what the relationship is between this and this. That's just to say that the vector that points out is going to be the same as the negative of the vector that points in. Okay. So Eric says, I've probably asked this before, if the force equation F is equal to QE plus QV cross B from the notes, for this exam, does the QE part just fall out, or for the purpose of our class, can we sweep it under the rug? So in general, you're right, there should be some QE vector here, because this is what Lorentz force law says. It tells you what the force is acting on a charge due to both its motion in the presence of a magnetic field and the presence of an electric field. But here, there is no electric field. There is no electric field. So something, yeah, I don't know how I would incorporate an electric field into this. I mean, I guess I could say, I could say there is no pipe. What should the electric field be in order for the particle to just fall without moving in the horizontal direction anymore? That's actually an interesting exam question. But it ultimately gets to the same idea. You find what the magnetic force is, and in that case you would need some electric force to balance it. But to answer your question a little bit more directly, the reason why this isn't here is because there's no electric field. This term is here because there's a magnetic field. But what I could say instead, what if I had some electric field, E0? How would that change this problem? Well, the problem would change so that instead of keeping this part of the Lorentz force law and getting rid of this part, then the force would only be from the electric field. So it's really based on what fields are given in the statement of the problem, and that's why for the problem that we just did, there's only the force from the magnetic field and no force from the electric field. Okay, yeah, that's a good question. Okay, so the next question concerns what I would call the third way of having some magnetic flux that's dependent on time. So I told you in the notes that there are three ways that you can get some time-dependent magnetic flux, and we had seen two of them already, but we haven't seen this third case. And so we can see why there are three cases if we consider the equation for the magnetic flux. So that's to say that phi sub b is equal to the integral of b vector dot dA. So one way that we could get some time dependency in this magnetic flux is if b is some function of time. So b a function of time. This is the first way. The second way is if a changes with respect to, that's WRT is with respect to time. The third way, we could keep the magnetic field and the area fixed in time. Well, they wouldn't change with respect to time, but the orientation of the two of them would change. So changing orientation of B with respect to A. Okay. And so the way that I got at changing the orientation of B with respect to A was to consider you have some loop that, let me see how I parameterize this. This has a radius of A, a radius of lowercase a, some resistance of R, and it's in the presence of a magnetic field that's a constant magnetic field pointing into the page. So B vector is going to be equal to B0 in. And now what I do, if I look at this just flat in the plane of the board, there is no changing magnetic flux, right? Because all the magnetic flux that you get from this static system where it's just sitting here it's going to be the same because the loop's not changing, the magnetic field's not changing. So in order to get some change out of this, what I'm going to do is I'm going to spin the loop. So I'm going to take this loop and it's going to rotate around this axis. So if I'm the loop, it's going to do something like this, right? So this is my, I mean, you can see my lack of grace. This is why I do physics and not ballet. So we can change the orientation of B with respect to A. And really what that's doing, when we evaluate this dot product, in general what we can say is that this is B dA times cosine of theta, where the time dependency now is going to come into the fact that theta changes with respect to time. Okay? So in this problem, I tell you that this is spinning at some constant angular velocity. We can find what the angle is as a function of time by considering that omega, by definition, is an angular velocity, which means that this is going to be d theta dt. We can multiply both sides by dt and integrate. And when we do that, we end up finding that theta of t is going to be equal to omega t, in general, plus some constant integration. But we're going to say that the initial angle was 0, and so theta of t is just this. Okay. So now when we, ultimately, what I should have done to start with was to write down Faraday's law, because that's where we're going with this. So Faraday's law says the integral of E dot dl is equal to the negative partial derivative with respect to time of the integral of B dot dA. And what I was getting at here in talking about how theta changes with respect to time was to parameterize this, this cosine of theta that I get out of the dot product. And so the next thing that I'm going to have here, this is going to be minus partial derivative with respect to time, integral b0 times cosine of omega t times dA. Okay? Now, when I look at this, dA for a circle is just going to be 2 pi r dr. And the important thing to take away from this is that I'm integrating with respect to r. And because I'm integrating with respect to r, none of this has any r dependency. B naught is just a constant. Cosine of omega t is not dependent on r. So I can bring that on the outside of the integral. And so this says this is going to be minus partial derivative with respect to time, b0 cosine of omega t times the integral of 2 pi r dr. Now, to evaluate this integral, we need to remember that this is really a definite integral that's parameterizing the area of this, this loop of wire that I have here. And so what that means is that this begins at 0 and goes out to the radius a. And so then when I do this, this integral here, I'm going to end up finding that this is going to give me a pi a squared divided by 2 times the 2 that I have here. And so this says, then I'm going to plot everything that's a constant. This is minus b0 pi a squared divided by 2 times 2, and that just goes away. And now I have the partial derivative with respect to time of cosine of omega t. Okay. Now, what is the partial derivative with respect to time of cosine of omega t? Personally, I never remember this exactly, but I remember what these look like. So this is going to be cosine, this is going to be sine. So the derivative here is going to be 0, but it's changing from being positive to being negative. And so that means that this is going to give me negative negative omega sine of omega t. So that's going to make this plus b0 pi a squared omega times sine of omega t. So this is going to be the right-hand side of Ampere's law. Of Faraday's law. Now the left-hand side is just going to come from, and I swept a little bit under the rug here, and that's to say that I chose my dA to be into the board so the dot product was positive. So that's going to give me a positive instead of a potentially a negative sign. And that's going to fix the direction of my dl, which is the direction of my loop, and I'm also going to say my current goes around that direction. And so when I go around the loop in this direction, on the left-hand side, I'm going to have just I times R. And so the last thing we want to do is to solve for what the current is as a function of time, and that's just to say that I is going to be equal to this divided by R. Okay? And that's it. Now, somebody was asking me about how can you check the way that Lenz's law works for this, and you can, but it's difficult to do. because of the functional dependence on T. Because this is the current is dependent on the sign, and the magnetic flux itself is related to the cosine. These things are going to go like this. So this would be a plot of the magnetic flux as a function of time, and this would be a plot of the current as a function of time. So what this says is initially the magnetic flux is going to be decreasing, right? It starts oriented like this, and then when it starts to turn, I'm going to have less magnetic flux than when it was just exactly in the same, when I had B and dA in the same direction. So that's going to decrease, and to make up for that decrease, the current is going to increase in the direction such that it preserves the magnetic flux that it had initially. And so if this spins like this, and this current goes around this way, this current's producing producing a magnetic field that is going to go in, and I'm losing magnetic field going in when I'm spinning like this. And so that's how you can check this. But again, the thing that's a little bit tricky about this, I'm considering exactly what's happening at the beginning. But as time goes on, this current's actually going to flip directions. And the reason for that is I'm going to get to a point where I'm like this, and then I'm increasing the flux again, right? So then when I'm increasing the flux, the current should act to oppose that increase, which is why the current's constantly changing directions as I'm going from the point where I have all of the flux to none of the flux, back to all of the flux again. Okay. So like I said, Lenz's law is a little bit tricky to check for this, but you can do it if you're careful with the way that you're writing or the way that you're using your right-hand rule and evaluating your dot products, and then if you plot these. I always think that plotting is a very good tool to check your work, because you can visually see what it is that the equations are telling you. I think that's part of the difficulty that people have with mathematics and physics, because it can be very abstract sometimes. But there's always a picture that you can draw to go along with the mathematics, and that many times makes it make more sense. Okay, so go ahead and take a look at this. I'm going to grab a drink of water, and let me know if you have any questions about this before we move on to the next one. Okay. So let's take a look at the next one. So the next one's it's a pretty tough one, but as long as you're following the rules that we laid out, it actually isn't too bad. But the interesting thing about this one, it actually combines three of the equations that we've used so far. And so we'll see how that works exactly. So it tells you that you have some infinitely long horizontal wire that has some current flowing to the left that's given by I of t is equal to I0 times t squared divided by tau squared. Okay. Now, the first thing that you want to do here, or the first thing that it asks you, is to find what the direction of the magnetic field is above the y, and what it's how it varies with the radius. So find the magnetic field produced by this wire, and specifically what direction is it going to be, and what is its value for distances that are above the wire. Okay. So in order to do this, what we're going to do is we're going to apply Ampere's law. And so Ampere's law is one of the two laws that we have for finding what magnetic fields are from currents, the other being the Biot-Savart law. You could use Biot-Savart here, but the reason why you don't want to is because I made this infinitely long, and that gives you the right type of symmetry to be able to do this without having to break this up into tiny little pieces and then think about all the vectors. You can do this just in terms of Ampere's law. Okay. So whenever we use Ampere's law, the first thing we want to do is to draw some Amperian loop. And the loop that I'm going to draw uses the right-hand rule, because what I'm going to say is I can take my thumb and point it in the direction of the current, and the magnetic field is going to wrap around in the direction of my fingers if I do that. And so when I do that, that says that the loop is going to go around like this, where, let's say that this is like the front of the loop. I need to be a little bit more consistent with this. But this is what it looks like, right? Is it dark? No. Goes the other way. Goes this way. Okay. So that's the direction of the loop. So it's going around like this. Okay. So when I do that, this loop has some radius of r, and I can evaluate the left-hand side of Ampere's law because I say that for every little infinitesimal dl that I have here, the magnetic field is in the same direction, which allows me to say that the integral of b vector dot dl vector is going to become b times dl. And then the variables that dl are written in terms of are not the variables that b varies over. So the magnetic field, another way to say that is the magnetic field has the same value at every point around this loop. So I can pull the b on the outside of the integral. This is the integral of dl over the closed loop. Because this is a circular loop, the integral of the closed loop for dl is just going to be the circumference of the circle, and so this is just going to be 2 pi r times b. Okay. Now, the last thing we need to do is evaluate what I in is. In this case, it's pretty straightforward because the only current and all of the current that goes through this loop is going to be the current that I give you here, just the I of t. And so this is going to say that this is mu0 times I0 t squared divided by tau squared. And so then I can solve for b by dividing both sides by 2 pi r. And so this is going to be equal to mu naught I naught t squared divided by 2 pi r tau squared. And because I want to make this a vector, and I also want to know what the magnetic field is in the plane of the board above the wire, this is just going to be pointing in. So this is going to be going in. Okay. And if you don't see this right away, think about what's happening here. The magnetic field is going around the loop like this. And when it's in the plane of the board, that's when it's going directly in. Okay. This is going to be important when we're doing the next part. Okay. So here's our magnetic field. The next part says, if we have some square loop of wire above here that has the bottom is some distance d away from the wire. This has some length of L and some, let's say, some height of h. Yeah, some height of h. We want to find what the current is that flows around this loop of wire. That's ultimately induced by the fact that I have some changing magnetic field because this magnetic field changes with time, right? This is our case 1 for Faraday's law. This is a magnetic field that changes as a function of time. Okay. So now what we can do is we can write down Faraday's law. So the integral of E dot dl is equal to the negative partial derivative with respect to time of the integral of B dot dA. Need a better piece of chalk. And then let's go ahead and, like I usually do, start by evaluating the right-hand side. Because B is pointing into the board, I'm going to choose dA also to point into the board. And by choosing dA going into the board, that fixes the direction for dl. So dl is going to be going in this direction, right? If my dA goes this way, thumb in direction of dA, dl goes around that way. I also say that my current goes around the same way. Okay. So that allows me to take the right-hand side of Faraday's law and then write this as negative partial derivative with respect to time of the integral of B times dA. Okay. Now, the next thing that I want to do is I want to explicitly evaluate this. And so in order to do that, I need to take the magnetic field that I solved for in the first part and plug it in here. And also realize that dA is going to have a little piece dx and a little piece dr. So this was a point of confusion talking to some people in class today, but I want to clarify this. The reason why this dA has to have a part dx and a part dr is because the magnetic field varies as I move further away from this wire. And so when I say what dA is, really what I'm trying to do when I'm finding the magnetic flux is to find out how much magnetic field is going through the whole loop. But for every position I put one of these little squares, I have a different magnetic field. So I have more magnetic field here than I do up here, right? Because this varies as 1 over r. So the closer I am to the bottom wire, the more magnetic field I have. But the more I move up, the less I have. Which is why it's important when I'm going to do this integral that because my magnetic field is dependent on r, my dAs also contain a dr. Okay? So let's go ahead and plug everything in here. So this is going to be negative partial derivative with respect to time. And actually, before I do this, I'm just going to pull out everything that's a constant. So this is going to be minus mu naught, I naught, 2 pi, tau squared. Those are all constants. So this is going to be minus mu naught, I naught, divided by 2 pi tau squared times the partial derivative with respect to time of the integral of, I still have my t squared, so I have t squared divided by r squared, and now I said dA is really dx dr. So this is dx dr. Now I need to put in some limits of integration. I'll show you how I break this apart as well. So my limits of integration I'll write in the next line. So this is going to be minus mu naught I naught divided by 2 pi tau squared. I'm also going to pull my t out here. I can't move it past the time derivative, but since this is an x and this is an r, the time isn't a factor in this integral. So this is really partial derivative with respect to time of t squared times the integral. Now I can, because the limits of integration here are not going to be related to each other, since this is a box. If this was like a triangle or something, then the limits would vary with respect to each other. I can break these apart and then do the two integrals independently of each other. So let's just say that this is dx times the integral of dr over r. And now I just need to write in my limits of integration. In x, this begins at 0 and goes up to L. And in r, this begins at d, so this is the distance d, and it goes up to a distance of h plus d. So this goes from d to h plus d. Okay? So now I just need to do these integrals, and like I said, these are independent of each other, so it's just the product of two one-dimensional integrals. And I'll also take the time derivative while I'm at it. So the time derivative is just going to give me 2t, so that's going to cancel a factor of 2 here. So this is going to give me minus mu naught I naught t divided by pi tau squared. My integral with respect to x is going to give me an L. My integral with respect to r is going to give me a natural log evaluated at h plus d minus evaluated at d. And so this is going to give me a natural log of h plus d divided by d. Okay? Now this is going to be the right-hand side. To evaluate the left-hand side, I say that the loop has some resistance of R, so there's some resistor here. And my current and the direction of the loop, because remember the direction of the loop is parameterized by dl, so that's the direction of my loop. I chose these to be in the same direction, and so this says that I times R is equal to this. Okay. Very nice so far. And the last thing I need to do is just divide both sides by R to solve for the current as a function of time. So I divide both sides by R, and then there you have it. Okay. Now, let's see if this checks out with what Lenz's law would say. So I have some current that is, or sorry, where's my magnetic field? My magnetic field is here. This magnetic field is going to be pointing in, and it's getting larger and larger as time goes on, right? Because if I plotted what this looks like as a function of time, this is b as a function of time, and this is time on my x-axis, it looks like this, right? Because This is just not a polynomial, a quadratic, right? So this magnetic field is increasing, and it's getting more and more magnetic field going in this direction. And so what the loop wants to do is it wants to produce a magnetic field that opposes that, right? Because I'm getting more and more magnetic field in this direction. The loop doesn't like that. It's going to produce magnetic field going this way. And so in order to get the magnetic field that goes to oppose the change, I need to have a current that's going to go around in this direction, right? So, and we can see that if I draw this direction here, imagine the current goes that way. Thumb in the direction of current, curl in the direction of the magnetic field that it produces. That gives me a magnetic field that points out to oppose the one that's increasing going in. Now, when I solved this problem, I actually had chosen to have my current go the opposite direction. But aha, there's a negative sign here. And so the negative sign actually tells me that the direction that I chose for the current is not the direction that it actually goes in. And with this negative sign and having the current go in the counterclockwise direction instead of the clockwise direction, it follows exactly what we would expect for Lenz's law. Okay, so I'm going to pause here and move some stuff around because I'm running out of room on the board, but let me know if you have any questions about this one. So I need this current, and I'm going to put that, I'm going to put the current over here. So I of t, and actually now I'm just going to write it with just the positive sign. So I of t is equal to mu naught I naught t divided by pi r tau squared L ln of h plus d divided by d, and then this was the loop. So we had the loop here. Shit, I lost my magnetic field. So the magnetic field was the other piece that I needed, and that goes over here. So b vector t is going to be equal to mu naught I naught divided by 2 pi r t squared over tau squared pointed in. Okay. So we have everything. So I'm just moving things around so that I can do the third part of this problem. Okay. So what the third part asks, and I'm only actually going to do two parts of this, is given now that this is the current that's flowing around this loop, and the magnetic field that's produced by the lower long wire here is going to be of this form. Find what the force is that acts on each element of this loop. Okay. So, like I said, I'm only going to do two of those. I'll do the bottom one. I'll do the right one, and you'll see why ultimately it's a little redundant to do all four of them, because you can see what's going to change for the calculation. So let's first start with the bottom one and write down our general equation for finding what the force is on some loop of wire. So that's, or some finite length of wire. So dF is going to be equal to I dl cross B, where dl is the little piece of path with some direction that parameterizes the direction of the current. B is the magnetic field that it's in the presence of, and what we're trying to do is find what the force is acting on this. So to do this first piece right here, dl is going to be, it's in the x direction, it's going to be some little piece of x, so it's x hat dx. Okay. So to do the right-hand rule here to find the direction of the cross product, ultimately the direction of the force, dl points this way, the magnetic field points in, so dl cross B gives me a force that points up. So that's the first thing. So we can say that this force is going to point in the y-hat direction. Now, let's plug in what these things are to evaluate this. And so this is going to be the current that flows through this. So I'm just going to put this as I of t. I'm not going to write the whole thing again. I of t times dx times the magnetic field. And I will write in what the magnetic field is. This is mu naught I naught t squared over tau squared divided by 2 pi. Now this r, for every point on this wire, for this first piece right here, this 1, you have the same distance from the wire. This is always the distance d that I had here. So this is the distance d, this is distance h. So when I plug this in, this is actually just the magnetic field evaluated at d. Okay. Now, in order to find what this total force is now, I just need to integrate this with respect to x from 0 to L. So when I look at this, I see that everything in this integral is independent of x, right? This isn't dependent on x. This I of t is not dependent on x. And so what that says then is I can pull everything else outside the integral, and this is just the integral of dx from 0 to L. And so this is just going to be I of t times times L times mu naught I naught divided by 2 pi d t squared over tau squared in the y hat direction. So this is the force acting on the element 1. Okay. Now, if I wanted to find the force acting on element 3, the force acting on element 3 is going to be the same, only it's going to be in the minus y direction, right? Because I can fingers in the direction of dl, curl into b. That's going to give me a force that points down, and it's at a different distance from this wire. So instead of being at the distance d, this would be at the distance d plus h. So those are the two differences. You get a negative sign, and this d instead would be a d plus h. Okay. Now let's look at the second piece right here. So this is 1, f vector 2. Okay. Now for this one, this is the direction of dl. So dl is really an r hat dr, right? Because it's going in the radial direction, and I'm defining the radial direction to be away from this this wire that forms some axis here. And so when I write this portion right here, when I write df2, this is going to be equal to the same current I of t. Now this is going to be an r hat dr cross b as a function of r. Okay. When I do the cross product, fingers in the direction of dl, curl into b, gives me a force that goes this way. And so this is going to be in the negative x hat direction. But now when I want to evaluate this integral, I see something kind of interesting here. And that's that when I do this, I have a dr, so I have my I of t. I have a dr, and then when I plug in b, I can't plug in b evaluated at some distance, because every point along this portion of the wire has a different magnetic field. And so what that means is I need to plug in mu naught I naught t squared over 2 pi r times tau squared. So now when I look at this, I do have something in the integrator that's dependent on the variable that I'm integrating with respect to. And these limits of integration are going to go from d to d plus h. D to d plus h. Okay. So now I can pull out everything that's not this r. I have another natural log that I'm going to see here. And so this is going to be equal to minus I of t times mu naught I naught t squared divided by 2 pi tau squared times the natural log of d plus h divided by d. Okay. And this was in the minus x hat direction. So I have my minus sign, and there's my x hat. Okay. Yeah. So this is a really important point, and it's quite likely. I haven't written the exam yet, but it's quite likely that that this is something that's going to come up. That if I wanted to find the force on this element of the wire, it's integrating a constant. Whereas if I wanted to find the force on this element of the wire, the magnetic field varies in the direction of that r hat. So that means that when I do this integral, I have to integrate over the magnetic field as a variable of the radius. Okay. So let me pause for a minute, and if you guys have any questions, let me know, and then I'll go on to the last one. Okay, so the last one, and really this is, the thing that's different about this one is instead of having a resistor, I have a capacitor now. But it still kind of follows the same kind of idea that we had for when we did the time-independent circuits. Namely, that evaluating for whatever circuit element I have just ends up being the loop rules that we had used before. So this question says, consider some magnetic field given by B of t is equal to B0 e to the minus t divided by tau, and that's going to be pointing in. And I tell you that I have some rectangular loop of width of w and height of h, and there's some capacitor that I put here. So this capacitor has some capacitance C1, and what we want to do is we want to find what the charge is on this capacitor as a function of time. So in order to do that, we'll start by writing down Faraday's law. So the integral of E dot dl is equal to the negative partial derivative with respect to time of the integral of B dot dA. Again, the way that I prefer to do this is to make this so that this dot product is positive. That means I have to choose dA going in the same direction as B. And so dA for me is going to go in like this. In doing that, I force a choice for the direction of dl. So dl is going to go this way. And I'm also going to say that because of that, the current goes this way. So current's going to go the same direction as dl. But that means if the current goes around this way, and we use conventional current, which says the positive charges are flowing, then this is going to be some plus q on the bottom, and this is going to be a minus q on the top. We'll see how this comes into play after I evaluate the right-hand side. Okay. So now, in order to evaluate this right-hand side, I've seen that I already have my dA and my b vector in the same direction. That says that this is going to be minus partial derivative with respect to time, integral b times dA. And now I can just plug in what my magnetic field is. This is going to be B0 e to the, be my negative partial derivative with respect to time. Negative partial derivative with respect to time of the integral of B0 e to the minus t divided by tau times dA. Now, this dA is just going to be some dx dy, right? So this is a dy, and this is dx. Or if you wanted to use the same convention that we had before, you can say this is dr. It's just a label. But what we see here is that this isn't dependent on any of the variables that we have here. So we can pull it outside the integral. So this is minus partial derivative with respect to time, b0 e to the minus t divided by tau, integral dA. The integral dA is just going to be the width times the height. And so then this is going to be equal to minus, I'll move the b0 over here as well. So this is b0 times h times w times the negative partial derivative with respect to time of, or just the partial derivative with respect to time, I have a negative sign over here, of e to the minus t divided by tau. The derivative of this is just going to be negative 1 over tau times e to the minus t divided by tau. And so this says in the end, this is going to be plus b0 hw divided by tau times e to the minus t divided by tau. So we've taken care of the right-hand side of Faraday's law. So let's look at what's going on with the left-hand side. Well, I defined this to be a plus cube here and a minus cube here. DL is going to go around in the clockwise direction, so that's my direction of the loop. And so when I go around this loop, the only thing that I see here is the capacitor, right? I get to the capacitor, there's no resistor here, there's no battery here. And so what that says then is that, that when I go around this loop, I'm just going to get this is going to be Q divided by C. Okay. So to find the charge as a function of time, that's just to say that Q of t is going to be equal to this times the capacitance C1. Okay? So that's what my charge is as a function of time. Okay? Now, the next thing that I can do here is I can find what the current is as a function of time. So the current as a function of time, I of t, is just going to be the derivative of the charge as a function of time with respect to time. Okay? So this is going to be dq dt, and so this is just going to be, when I take this time derivative, I'm going to get a negative 1 over tau, so that's going to give me tau squared in the denominator, and so this is going to be minus C1 B0 H W divided by tau squared e to the minus t divided by tau, and then that's it. Okay. So that's my current. The last thing that I want to do is find what the force is on each side of the rectangle. And so in order to do that, what we need to see is that I have some, I mean, this follows almost exactly the same as the last problem. The thing that makes this a little bit simpler is that this magnetic field is not dependent on the position at all, right? It's only dependent on the time. So when I do these integrals for df is equal to I dl cross b, this is going to say then that my hold on a second. Something funny is going on here. So I get a negative sign with my current, which means that the current actually is going in the opposite direction. That would produce a magnetic field going out, but we want a magnetic field going in. I think I made a mistake with a sign somewhere. I think I might have made a mistake with a sign somewhere. This current has to go in the direction that I defined it actually, because this is, if I plot what this magnetic field is and by association what the magnetic flux looks like, this is decreasing with respect to time, and so because that's decreasing, whatever the direction of the current is needs to be such that it needs to be such that it preserves the magnetic field that was there that it's losing. So this is the correct direction of the current, but I'm not seeing why I'm getting a negative sign here. It's probably because this needs a negative sign, but it's not apparent to me why that's the case. So don't worry too much about that. There's something funny going on with the function that I chose here, and I'll think about this more, and hopefully I'll have an answer for you tomorrow. But I think because I chose this e to the minus t over tau, my charge. What this says actually is that at t is equal to 0. Yeah, there's something funny going on here, because what this says is I have to have a charge on this plate before it starts. Because evaluate this at t is equal to 0. That gives me e to the 0, which is 1. So the charge at t is equal to 0 is equal to 0. But if I'm making the assumption that it's not 0, I have to do something funny with the boundary conditions in order for this to work. This is more complicated than something that I should ask you at this point. And if you're interested, I can talk to you a little bit more about why I'm saying that. This is really getting into the time-dependent circuits. If I wanted to go the route of talking about what I of t is, And that's ultimately this IFT does have to be negative because there has to be a charge on this initially if the charge as a function of time is this. Yeah, I'm a little bit more satisfied with that. But yeah, for the sake of this problem, I asked you more than I should have because for the particular function that I have here, it doesn't quite work out. So don't worry about past this point. It's only up to here. It's only up to here. And then everything else is fine. The important thing to take away from this is the Faraday's law analysis. You have to be very careful with your negative signs for Lenz's law to work out. But you can use Lenz's law, and that's ultimately what I did here, and how I found the fact that there needs to be an extra negative sign here by applying Lenz's law, because I know that the magnetic flux is going to be decreasing because this is the function of the magnetic field, which means that the direction of the current should be the direction that I have it here. But when I take a time derivative of this, I get an extra negative sign because I had a negative sign up here, which is why I have that here, which ultimately means that I need a negative sign there to make this positive in the end. So probably a lot to follow. So like I said, don't worry about this. This piece is the most important piece, and that just kind of follows from the things that we've done already. Okay. Any other questions about these, or other questions? Somebody asked me a question earlier today or in via email that I didn't have a chance to get to. So I got another 5 minutes or so. So I'll answer one more if somebody has another question. Yeah, that's funny. That's funny. Yeah, this has to be negative. This has to be negative. Why is that the case? That means that the charge has to be inverted from the direction that I have it written. That's not actually the direction that the charge would be oriented in originally. Anyway. Okay, so that's it. I'll see you guys tomorrow. We have some more of these Faraday's law questions that we're going to be doing in recitation. Wednesday, we are going to have even more Faraday's law questions. I think those are probably the harder things that are on the exam. Thursday will be a review. So I think we'll be good and prepared for it. And when I write the exams, I'll be a lot more careful about the functions that I choose for this. This question I put together a little quickly. I didn't check how this part worked out until now, actually. Okay, so I hope everybody has a good night, and I'll see you tomorrow.